Hi, everybody. Today we're going to be talking about forces. We're really going to get into what is causing motion, or what is changing motion, really, is what we should say with forces. So what, first off, is a force? So a force is a thing that will change the motion of a body or will counteract another force and make sure that it holds in place. Okay, now that seems like a weird little addendum to throw on there at the end, but you'll see why a little bit later. Another simpler definition of a force, of course, is just a push or a pull on an object. There are two basic kinds of forces, and we say that you have contact forces where you actually touch another thing, like kicking a soccer ball, like throwing something, like slapping your hands together or something, right? Or you have non-contact forces, and those are forces that act at some distance. So think gravity, right? You can jump off the ground and gravity will still pull you down even though you're not in contact with the ground. Magnets can, of course, act on one another even if they're not touching. Now, what's kind of strange and weird to think about is there really actually are no such things as true contact forces. In fact, every contact force that you can think of is really the sum of a bunch of electrostatic interactions generally, meaning like electrons are pushing on one another, right? And electrons never actually come into contact with one another. They simply cannot do that because, remember, they are both negatively charged, right? So if you get a whole bunch of negatively charged things, a bunch of electrons, like in your hands, close to a bunch of other electrons, like your other hand, they will push against one another. They will repel one another. And so it feels like you're touching your hands together. In reality, they never actually do touch, which is a little bit strange to think about, but it is true, unfortunately, that you can never really touch anything. Now, don't try to take that into too literal of a sense. We still consider it, punching somebody if you put your fist close enough to their face that it hurts their face, but technically you are not actually touching them. So one thing that we can also say about forces is they are vectors. And we know that all vectors have a magnitude and a direction. And this is going to be really important for forces because we are going to spend a lot of time diagramming forces as vectors, as what we'll later call free body diagrams. We'll show the forces on that diagram. And so, of course, we do vectors with arrows, and you know how to do that, right? The length of the arrow is the magnitude, and the direction of the arrow is the direction of the force, of course. So here are a couple of, three forces acting on one thing. So imagine three people pushing on a table. One of them pushes to the right or to the east. One pushes to the west. One pushes to the north, right? And so you can see the three vectors that I've drawn. This is the one pushing east. This is the one pushing west. And this is the one pushing north. And you might ask yourself, well, what is the net result, right? If you imagine two people pushing on a table from opposite ends, and then a third person pushing from a totally different direction, right? The two people pushing from the ends are going to cancel each other out, right? So this 3 Newton force and this 3 Newton force will cancel each other out, but there's nothing canceling out this force. And so the net force, the net action will be pushing in this particular direction, right? So any change in the motion of this, in this case, a table, would be in this direction, okay? Now, we also group forces by what sort of causes them and what's actually happening in the force. And so you'll often hear that there are four fundamental forces. When people speak of 4 fundamental forces, the 4 they're talking about are the 4 you see there: gravitational, strong nuclear, electromagnetic, and weak nuclear. It actually turns out, though, that 2 of those forces are the same thing. So the electromagnetic force and the weak nuclear force were, I believe it was in the 1960s, they were actually determined to be the same thing. So some guys, I believe Steven Weinberg was one of them, actually won a Nobel Prize for determining that these were actually the same thing. They called it the electroweak force. So in a sense, you really just have the gravitational, the strong nuclear, and the electroweak force. So truly there are now three fundamental forces. One day, the hope of physicists is that we will be able to unite all of these forces, be able to describe them all in one set of equations, and therefore we'll have a unification of the forces, and they call that a GUT. They would call that a grand unification theory if we could do all of that. So far, no dice. They haven't figured out how to do that, but work is, of course, still working. They're still going at it. That's fundamental physics, though. That's a really interesting area. We're not that worried about grand unification in this class, but I just think it's kind of interesting. Those are your fundamental forces. They are the forces that everything is built out of. So any motion, any changes in motion that you can think of are caused by some combination of those forces. So you might ask, well, what about when I kick a soccer ball, right? What's causing that? It's not gravitational, right? The kick isn't gravitational. Of course, the pull toward the ground that the ball will experience is. The strong nuclear force is really not what's causing the ball to move, right? It's really the electromagnetic force in that case. So it's actually, once again, I mentioned, the electrons in your hands hitting, right? In this case, it would be the electrons in the ball, and the electrons in your shoe are really the ones that are coming so close to one another that they are causing the force that is pushing the ball along. So that's what we call a non-fundamental force, is the actual kick. And so it's just the result of the sum of the fundamental forces that are acting. One distinction that we need to make is the difference between mass and weight. In this course, we will use both terms. In chemistry, hopefully you only were taught to use the word mass, generally speaking, because in chemistry, you just measure mass. You don't really measure weight. But in this course, we need kind of both things, all right? And so there is a fundamental difference that you need to understand between these. Mass is the amount of stuff that an object possesses, right? Like, my body has more mass than, a grapefruit, right? If there's more stuff in me. There's more electrons, protons, neutrons, etc., right? In me than there are in a grapefruit, even though me and the grapefruit are actually made out of a lot of the same elements, right? I've just got a lot more of them, okay? But weight is a different thing. The grapefruit could weigh more than me. It could, depending on the situation, right? So if I was to go into outer space, maybe to, a planet with very low gravity, then the force of gravity acting on me, my weight would feel very, very light. And whereas the grapefruit back on Earth might actually have a much higher weight. So the force that gravity is pulling on that grapefruit with might be more. It really might be. So weight and mass are, of course, highly correlated, right? The heavier something is on Earth, right, the more weight it has, the more mass it also will have. But they are not the same thing. Right? Mass and weight are definitely not the same thing. Weight is actually a force. It's actually a vector, and it's always pointed toward the center of the Earth, whereas mass is not a vector. It's just a scalar. It's just the amount, right? It's just counting it all up, counting up the number of electrons and protons and neutrons and just summing all that up. That's how you get mass. Okay. Now, we have a couple of laws of motion, all right, thanks to old Isaac Newton. And they are very useful. They're very interesting. One of them, the first one, we call Newton's first law of motion, says, well, it's often referred to as the inertial law, right? The inertial law, meaning that if you have no net force, right? If you have no net force, then if you're at rest, you're going to remain at rest. If you're moving, you're going to continue to move in exactly the same way that you always were. Now, these are technically equivalent statements. They're a little bit redundant to say, right? A resting object will continue to remain at rest, and a moving object will continue to have the same velocity. They're really the same statement. There's the same statement in the sense that if you have no net force, you have no acceleration, right? And therefore you can't change your velocity. So if you're at rest, not changing your velocity means you stay at rest. If you have a velocity already, not changing your velocity means you have the same velocity, right? So so pay attention to that, right? No net force, no acceleration, no change in velocity. That's really what this is saying. So let's say you jump out of a plane, right? You go skydiving. Well, at some point, you will hit what we call terminal velocity, right? And that's the point where gravity is going to be pulling you down, but at the same time, air resistance will be so strong because of your high speed. The higher the speed, actually, the higher the resistance air gives. And so you will eventually kind of equal out, right? The air resistance will equal out with the force of gravity. And you will actually, you will have no net force on you, right? There'll be no net force on you. Now, does that mean that you keep falling, or do you cease to fall? Well, if you've ever been skydiving, you know that you continue to fall. What's different is that you don't accelerate anymore, right? And so what is this situation called? I already gave it away, right? This is called terminal velocity. It is, you're kind of stuck. This is the end velocity, the fastest velocity you can get to. So will you keep following? Yes. And this is called terminal velocity. Okay. All right. I'm going to have to pause this video, and we'll have to make a second video because I'm running a little bit.